All right, my stats people, welcome to the second section of Chapter 3, where we look at linear regression. And this section, Section 3.2, this is where we really start to look at calculation. So you're going to have to do just a little bit of algebra on this one. Mostly it's a lot of number crunching. But we're going to start with the familiar scatter plot like we did on our previous lessons. So here we have the data from one of the groups. And this group, poor group, they forgot to record their measurement for 5 rubber bands. Bummer. Well, we can still go to Staplet and make a scatter plot. And then we're going to click on Calculate Least Squares Regression Line. So let's take a look at that. Here is... gone ahead and I've already made the scatter plot here. Down over here, you're pretty used to that R squared already, but now we have the regression model. Okay, so here is our regression model. Up over here, you'll see that your Staplet has already gone and drawn in that line. And yes, the line does seem to be a really good fit for the data in this case. Over here on our notes, we can just copy and paste that over here. And you'll notice that although we have the use of 2 variables, in this case y and x, we don't have anything contextual to say about y and x. So we have to actually tell what y and x are. So y is the distance traveled, and x is the number of rubber bands. Now, this is not actually my favorite way to write down a linear model. What I would prefer that you write this in this format here. Now, in this format, you don't even bother with x and y. And that feels very unmathematical, but we are in stats. This isn't algebra, so we have the latitude to do something like this. So I would prefer that you write this as predicted distance. Don't forget the word predicted is equal to 25.333 plus 7.464 multiplied by the number of rubber bands. This saves you the trouble of having to, write down a definition for x and y. Now, incidentally, there is a funny looking symbol here, right over there. Zoom in on that. That is a symbol called y hat. It's called y hat, and the meaning here is the predicted value of y. Now, over here on the equation, notice that x doesn't have a hat, and that is correct in the context because we're never predicting the x coordinate. We're not predicting the number of rubber bands. We're predicting the y coordinate. We're predicting the distance. So if you should favor the x and y notation, and I'm telling you not to, but if you decide to do that, or if you ever read y hat, you should know that they're talking about the predicted value of y. So now that we have that, we can use a regression line to predict the distance that Barbie travels for 5 rubber bands. Let's show our work. I'm going to copy and paste my preferred equation here. I'll substitute 5, and we get a predicted distance of 62.653 centimeters. So with 5 rubber bands, Barbie is predicted to travel 62.653 centimeters. Now, important for you to know at this point that this is not an algebra class. You don't need to show me all of the steps in simplifying your equation down to 62.653. I know you have a calculator. The AP people, they know you have a calculator, and they're just assuming that you use your calculator to do all your algebra for you. So you should never get this wrong. because you don't know how to use order of operations. Chuck it into your calculator, get the question correct. Now, that said, let's move on to the next part here. And we're going to say that one group member forgot or found the measurement for 5, and they got 64 centimeters. So was the prediction in number 2, was that too high or too low? How far off was that prediction? This quantity is something that we call the residual, and it is the actual amount that was, done by your y coordinate, by your response variable, minus the predicted amount from your least squares regression line. Our actual is 64 centimeters. Our prediction was 62.653 centimeters. So we get a residual amount of 1.347 centimeters. And we can interpret that as the actual distance was 1.347 centimeters greater than predicted. Or the other way around, the predicted distance was 1.347 centimeters less than the actual distance. So it really kind of depends on, are we talking about the prediction or are we talking about the actual distance? And in this case, we're talking about the prediction. So the correct answer, the correct thing that we should be leaving here, would be a statement about the predicted distance. So the predicted distance was 1.347 centimeters less than the actual distance. So now we're going to predict the distance that Barbie would travel if the group uses 20 rubber bands instead of, well, we did 5 before. Let's get our predicted distance equation, our least squares regression line. Oops, you're not supposed to know that word yet, but yeah, this is our prediction. Substitute 20, and that gives us 174.6 centimeters. Now, would you trust this prediction more or less than this prediction over here with 5 rubber bands? And hopefully this is going to be less trustworthy, because when we calculated our regression, we only used 7 rubber bands, and 20 rubber bands is way different than 7 rubber bands. Since we're predicting far outside the range or the data that we used, this is a process called extrapolation. And extrapolation produces untrustworthy results. Now, I know what you're thinking. Maybe I know what you're thinking. Maybe you're thinking what I'm thinking. But when we do science, we're always talking about using our data to make predictions that's outside of our experience. That's the whole point of creating mathematical models in many cases. That always comes with a little bit of, with a grain of salt, because those results may or may not be trustworthy. We're going far outside of our data. So always, whenever you're using extrapolation, be a little bit careful about the predictive powers of that. All right, so a little bit less controversial. What about the y-intercept of the equation of our regression line? And that's going to be 25.333 centimeters. And now what does that mean? Now you can use this as a sentence starter, but when you have 0 rubber bands, or when 0 rubber bands are used, then that means the predicted distance is going to be about 25.3333 centimeters. I encourage you to use this fill-in-the-blank interpretation for the y-intercept whenever you need to interpret the y-intercept. Next, we go to the slope. So the slope is about 7.646 centimeters. And that means that for every increase of one rubber band, the distance traveled increases by about 7.646 centimeters. Just like before, this is a wonderful sentence starter, fill in the blank. So I encourage you to use this every time you need to interpret the slope. Let's get to our big ideas here. We have this idea of the least squares regression line, where we have y hat equals a plus bx. Now that's a good way of writing it, along with the, you're going to have to explain what x and y means, but this is a good way of writing it. The better way would be for the predicted response is equal to a plus b multiplied by the explanatory variable, and use words to say what the response and the explanatory variable are. I highly recommend you use that way. Now don't forget that the caret, that's called a hat, and it means predicted. Also, be careful with extrapolation. And we're using A and B for y-intercept and slope. And that's just the way that AP Stats likes to notate slope and y-intercept, with A being the y-intercept and B being the slope. Residuals, the residual is the actual minus predicted. Nicely, the first letters of that spell out the word wrap. And you have your sentence starter for that as well. And then you have your sentence starters for the y-intercept and the slope. For every sentence starter I give you, make sure that you adjust it for readability after you write it out initially. You do want the words you are writing to make sense. So here we go with check your understanding now. Some data were collected on the weights of male white laboratory rats for the first 25 weeks after its birth. A scatter plot of y equals weight in grams and x equals time since birth in weeks shows a fairly strong positive linear relationship. The regression model, y hat equals 100 plus 40x, models the data fairly well. Notice how this question keeps with the rules. If you're going to use y and x, you're going to have to somewhere define what y and x are equal to. So let's interpret the slope of this linear regression. For every increase of one, the explanatory variable is in units of time, weeks. The explanatory variable, what the explanatory variable is again, time since birth. The response variable, the response variable is weight in grams. Now the slope is positive, it's positive 40, so that means that the weight is increasing by about, and the number here is 40, and the units is grams. Now we're just going to adjust for readability. For every increase of 1 week in the time since birth, it seems a little bit awkward. Time since birth is probably better said as age. So for every increase of 1 week in age, the weight increases by about 40 grams. Maybe we should put additional context here because we're talking about a rat. So the rat's weight increases by about 40 grams. That sounds pretty good. Next, does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. If not, explain why. Well, if x is 0, if the weeks since birth is equal to 0, that would mean that that's when the rat was first born. So when that happens, it looks as though the predicted weight would be 100 grams. Does that make sense? Yeah, that kind of makes sense. Let's write that out. So yeah, the Y-intercept has meaning. Let's grab our sentence starter for the Y-intercept. The value of the rat's weight when the time since birth is 0 is 100 grams. That's just for readability. The value, I think the value here is kind of unnecessary. The rat's weight when the time since birth is 0, there's got to be a smoother way of saying that. The rat's weight at birth is predicted, I like that prediction part, predicted to be 100 grams. That sounds pretty good. Next, let's predict the rat's weight at 16 weeks old. Write the regression line, substitute, calculate, and interpret. Next, calculate and interpret the residual if the rat actually weighed 400 grams at 16 weeks old. Again, same thing. Let's write our equation. Then we substitute. Calculate. 400. Okay, so let's interpret the residual then. Just looking at the numbers, it looks like the predicted weight is greater than the actual weight. The predicted weight was 740. The actual weight was 700. So the predicted weight is 40 grams more than the actual weight. I highly recommend, rather than trying to memorize what a positive and a negative number means, just look at the values. 740, the predicted weight, is greater than 700 grams, which was the actual weight. So just explain what you see. Now, should you use this line to predict the rat's weight at 2 years old? That is, let's see, 2 years old. How many weeks is that? That's 104 weeks. Yeah, that's kind of far away from our values. We only have like the first 7 weeks, I think it was. 25 weeks, if I'm reading that. Yeah, we only have the first 25 weeks. 100 weeks is very far away from 20 weeks. We only have data for the first 25 weeks. Since 2 years, or 104 weeks, is very far from our data, we should not use the equation to make a prediction. This would have been an example of extrapolation. And that, folks, that is the end of 3.2 Day 1, our very first look at the mathematics behind all of our regression lines. So we'll see you next time here. Have a good one, and see you next one.